We want to use the Rawls theorem to prove the mean value theorem. And so we're going to begin the proof by creating the equation of the secant line using the point a f of a. Remember that we're talking about a continuous differentiable function and a bounded interval. So it's continuous over the closed interval and it's differentiable over the open interval, except I didn't draw an open sign. Here we go. And so with those facts stated, we know that the slope of the secant line is our quotient. So f of b minus f of a over b minus a. And we're actually going to put that into our linear function point slope formula. So if you remember the point slope formula, it kind of goes like this: y minus y1 equals m, which is this, parenthesis x minus x1. So we're going to fill this in with everything we need, and I'm actually going to add the y1 to the other side here. So we've got y equals our slope, and then since I've asked you to use the point a comma f of a, here instead of putting x minus x1, we're going to put x minus a. And then here instead of putting y1, we're going to put plus f of a. So this is the equation of our secant line. And remember, the secant line is just a line that connects 2 points on the curve of the function. Next, we're going to create a function that models the vertical distance between the function f and the secant line. And there's a reason for this, and often when you're doing a proof, you don't know these reasons if you're legitimately following through. The nice thing about being a mathematical student is that these proofs have already been determined for us, and we just need to understand them. So let's say that this is the function from a to b. That means this is the secant line here, and just assume that it didn't cross the function more than once, because that wouldn't work. We care about the vertical distance because the vertical distance will trigger Rawls' theorem. We know that at this endpoint and this endpoint, the vertical distance is both 0. And since it starts and ends with a vertical distance of 0, we can find a critical value in between where the derivative is equal to 0. And so this is going to be our proof. So g is our vertical distance. Well, to calculate the vertical distance, you want to do your function minus your secant line. And so our function is represented by f of x, or the vertical of our function is represented by f of x, and our secant we solved for in the previous problem. So we're just going to bring that down in all of its glory. F of a, b minus a, times x minus a, plus f of a. Yay! All right, here's where the proof really comes together. And if you want to see a better picture than mine, you can always check out the picture provided by your textbook. Since f is a differentiable function over the interval that we're referring to, g of x, which is just a difference between two f functions, is also going to be differentiable and continuous. So if you add or subtract two continuous functions, you're left with a continuous function. If you add or subtract differentiable functions, you're left with the differentiable functions. So we can be assured that g of x, which I actually didn't squeeze in here at the beginning, x is both continuous and differentiable. Well, that means that there has to be a point C somewhere on g of x where the derivative is equal to 0. So the derivative of g of x is g prime of x, which is equal to f prime of x minus the derivative of the secant line, which is just going to simplify to be its slope. But we know that g prime is equal to, supposed to be doing the derivative down here. We know that g prime is equal to 0 by the condition set by Rawls' theorem. So now we can say 0 is equal to f prime of x minus f of b minus f of a all over b minus a. And then add that to the other side. Equals f of b minus f of a all over b minus a. I'm actually missing a step in the proof, so let me erase this out. And this is, again, just getting that clear notation so that the proof really flows nicely. So up here we have g prime equals f prime minus the slope of the secant line, which is the derivative of the secant line. And then we know that there exists some point C. I did it again. Doesn't count if you catch it and fix it. C, where the derivative is equal to 0. And this looks better because when I said g of x and then jumped to 0, I'm really implying that the whole function is equal to 0, which isn't true. Only g prime of c. So there exists a c in the interval a to b such that g prime of c is equal to 0. And so we substitute c, and then we substitute 0, and then we know that f prime of c is equal to f of b minus f of a over b minus a, which, if it's been too long to remember, is the mean value theorem. That is actually the equation the mean value theorem provides us. So here's how we use Rawls' theorem to prove the mean value theorem. Later at the end of the page, I don't have any more examples, just a couple of corollaries, 3 actually, that I want you to familiarize yourself with. So make sure you're reading these proofs in section 4.4 of our online textbook. This concludes the notes for the mean value theorem. Thank you for watching.